Hello everyone, I am Dr. Sirajul Akfazi. I welcome you in my YouTube channel. Today in this video, I am going to talk about the lattice energy. So, lattice energy and its properties, determination of lattice energy calculation, comparison between both approaches, question answer and conclusions. So, where can lattice energy be valued? Lattice energy is associated with the many interaction as a cation and anion packed together in a standard lattice. For covalent bond, the bond dissociation energy is associated with the interaction of just two atoms. So, covalent compounds and ionic compounds. So, metallic compounds, ionic compounds will leak at the lattice energy. So, crystal lattice of the ionic compound. Electrostatic attraction is non-directional, no direction, direct anion cation pair. Therefore, there is no ionic molecule. So, the chemical formula is an empirical formula simply giving the ratio of ion based on the charge balance. You can see the sodium, chlorine, formation of sodium chloride, and del H is equal to lattice energy. Now, energies of ionic bond formations. Ionization energy of the metal is endothermic. Electron affinity of non-metal is exothermic. So, IE metal greater than EA non-metals. So, the formation of ionic compound should be endothermic, but the heat of formation of most ionic compound is exothermic and generally large. Why? You can see the heat of formation is equal to -787 kJ per mole. Now, lattice energy. The extra stability that accompanies the formation of the crystal lattice is measured as the lattice energy. The lattice energy is the energy released when the solid crystal forms from separate ions in the gas phase state. Always exothermic, hard to measure directly, but can be calculated from knowledge of other process. Lattice energy directly proportional to charge, inversely proportional to 1 by distance between ions. Now, properties of lattice energy. Melting boiling point, stronger bond, higher melting boiling point. Hardness, stronger bond, harder crystal. Order, stronger bond, weaker order. State at room temperature, stronger bonds are more likely to be solid and pseudoplatin. Now, determine the lattice energy. Calculation for lattice energy. Theoretical approach, experimental approach. Bond-Lande equation, Bond-Haber cycle. So, Bond-Lande equations in 1980, Max Born and Alfred Lande proposed the formula for the lattice energy calculation on the basis of electrostatic potential of ionic lattice and repulsive potential energy term. You can see this is the formula, and each term have the significance, meaning Avogadro number, Madelung constant, number of charge respective ion, electronic charge, permittivity of free space, distance to closest ion, and bond exponent. Now, Madelung constant and bond exponent. Consider sodium chloride structure for sodium plus ion. So, neighbors and distance. Neighbor 6 chlorine R naught, 12 sodium plus root 2 R naught, 8 chloride ion root 3 R naught, 6 sodium plus root 4 R naught, 24 Cl minus root 5 R naught. So, ion configuration in helium 5, neon 7, argon copper plus, and krypton silver plus, and xenon Au plus 2. So, derivation of Bond-Lande equations. You have the electrostatic potential and repulsive potential. E pair Z square E square divided by 4 pi epsilon 0 R. Each have their own meaning. Here B constant is scaling the strength of the repulsive interaction. Here R represent distance between two oppositively charged ions. Here N represent bond exponents. Exponents approx 5 to 12 express the stiffness of the repulsive barriers. So, A Madelung constant related to geometry of the crystal. Now, derivation of Bond-Lande equation. If you have the total energy EA plus ER, then this value and this value. Applying the minimization conditions, R is equal to R naught and this, then you have this formula, U R naught minus AZ square E square divided by 4 pi epsilon 0 R naught, 1 minus 1 by N. Now, drawback of Bond-Lande equation. Calculation for lattice energy was based on the Coulomb's law with considered ions as a point charges. In deriving lattice energy, the reductions of the charges due to their interaction are not considered. Now, modification of Bond-Land equation. Bond-Meyer equations, if you see, Meyer showed the E minus R by rho, where rho is the constant dependent on the compressibility of the crystal, giving a better repulsion term than 1 by R. Here UMB is equal to minus NA AZ plus Z minus E square divided by 4 pi epsilon 0 R 0 under bracket 1 minus rho by R 0. So rho 30 pm works well for the all alkali metal halide and other simple cases where R naught value are in MB. Now modification of the Bond-Land equation. Capacitance equations. In the absence of detailed structure data, equations can be used to estimate U. So each term have their own meanings. Now advantage of these equations. Give a good estimation. Real values differ in most cases by less than 5%. Used with ionic compound containing polyatomic ion as a means of calculating their thermochemical radii, in which the ion are treated as sphere. Useful for complex ion like sulfate SO4 2 minus or phosphate PO3 minus. If you check this one, nitrate, R value, iron, sulfate 2 3, and each have their R minus. Now experimentally determine lattice energy. The Born-Haber cycle is the hypothetical series of reactions that represent the formation of any compound from its constituent element. The reactions are chosen so that change in enthalpy of each reaction is known except for the last one, which is the lattice energy. So Born-Haber cycle use his law to add up enthalpy change of other reaction to determine the lattice energy. Del H salt, del H formation of metal atom, G, del H formation of non-metal atom, G, and you can see, so del H naught crystal lattice is equal to lattice energy. For the metal atom like this, so non-metal atom you have the anion, del H heat of formation of electron affinity. So this diagram will show something. You can see the sodium plus in gas plus Cl minus gas. So this is the hierarchy structure. Now lattice energy calculation for sodium chloride. According to his law, total energy change during the complete course of chemical reaction in the same whether the reaction is made in one step or multi steps. Heat of formation plus half D plus IE, EA and LS. You have each step and then you can calculate the lattice energy for sodium chloride MF2. So trend in lattice energy, ion charge. You can see the sodium plus charge is small and F minus is big. On the other hand, calcium 2 plus is small and O2 minus is big. So the force of attraction between oppositely charged particle is directly proportional to the product of the charge. So larger means ions are more strongly attracted. So larger charge, stronger attraction, larger lattice energy. So of the two factors, ion charge is generally more important. So lattice energy versus ion size. You can see the lithium, sodium, potassium and cesium increasing, and you have the Cl minus, which it is, though it is not increasing. So now you can see the metal chloride and lattice energy, how it is deviating. Now comparison between experimental and theoretical calculate lattice energy value. You can see 918, 912, theoretically 7870, like this. So which compound will have the greatest lattice energy, MgS or lithium fluoride? The magnitude of charge is the first things you should look at. Magnesium plus 2 charge, sulfide 2 minus charge. So lithium plus 1 charge, fluoride minus 1 charge. So magnesium sulfide has a greater individual charge, so MgS has the greater lattice energy. Now which compound will have the lower melting point, Na2S or barium oxide? A lower melting point means we need to select the compound with the lower lattice energy. We check the charges first. Sodium plus 1, sulfide minus 2. Beryllium 2 plus and oxide minus. So sodium sulfide has smaller individual charges, so it has the lower melting point. Now, which compound has harder crystal, calcium chloride or magnesium chloride? Harder crystal require higher lattice energy. First check the charge, calcium 2 plus, chloride minus, magnesium 2 plus, chloride minus. The charge are the same, so we need to see which ion have fewer energy level. So, which atom has the harder crystal, calcium chloride or magnesium chloride? The charge are the same, so we need to see which ion have fewer energy levels. So, calcium 4, chloride 3, magnesium 3, chloride 3. So, fewer energy levels give magnesium chloride higher lattice energy, therefore the harder crystal. Now, which compound has the lower boiling point, silver nitrate or potassium sulfate? So, lower boiling point means a lower lattice energy, silver plus 1, nitrate minus 1, potassium plus 1, sulfate 2 minus. Charges indicate lower lattice energy for silver nitrate. Lower lattice energy means lower boiling point. So, in conclusion, my friend, we have learned lattice energy and its significance, approaches to determine it, modification of the theoretical approach, experimental calculation, trend in lattice energy determination. If you like this type of video, then subscribe my channel, and thank you for your watching.